I'm Charlie Hunter.
I'm John Cryer.
I'm Kevin Nguyen.
I'm Emmanuel Bryan.
I'm Robert Hicks, and we're
Team Hermes.
Hi, I'm Charlie Hunter, and a member of Team Hermes. Hermes stands for Hyper Exoplanet Reconnaissance Messenger. The goal of our mission is to go to the Epsilon Eridani star system and explore the exoplanets there. Our mission is to send back photographs of the known exoplanet Epsilon Eridani b. Our estimated launch date is 2015, and the estimated time of travel is 53,000 years.
The propulsion system design we propose relies on a combination of a 3-stage launch vehicle, 3 RIT-22 ion thrusters, and some gravity assist maneuvers to reach a top velocity of between 185,000 kilometers per hour and 215,000 kilometers per hour. At these velocities, it's possible to travel 10 light years in between 53 and 62,000 years. We chose the RIT-22 thruster because they've been extensively tested and shown to have a high lifetime expectation. Also, they're capable of providing high specific impulse with only 7 kilowatts of impulse power. This propulsion system is capable of providing 10 to 30,000 kilometers per hour of additional velocity for this mission, as well as providing thrust for orbital maneuvers and for attitude control.
For the solar panel part, we will use a 100 square meter panel in order to have enough power in the habitable zone, but everywhere in the system too. So this panel needs to be high efficiency solar cells, but most important is to be a low temperature and high radiation resistant technology. That's why we choose gallium arsenide triple junction. Moreover, this panel needs to be modular in order to deploy the panel only once in the system. And so these solar cells will only be used once in the Epsilon Eridani system, and I will let Kevin talk about the power used in the travel port.
Since the ion drive propulsion system uses a lot of power, the solar panels array system is not going to be enough to provide power. Therefore, we have chosen to use a nuclear fission reactor, which is more efficient and cost-effective than RTGs. The nuclear fission reactor will be able to output a power of 5 to 10 kilowatts.
Epsilon Eridani is 10.5 light years away from Earth. To make up for the path loss over this very large distance, we need very high gain antennas on both ends. On Earth, we decided to use, for the receiver, the square kilometer array, which is set to be finished in 2024. This array of antennas has a collection area of 1 square kilometer, or 1 million meters squared, which leads to a very high gain. On the satellite, we decided to use a 10-meter circular dish to transmit towards Earth, another very high gain antenna.
So since our spacecraft is going to be 10.5 light years away, we need a very robust modulation scheme to effectively transmit data back to Earth. For this reason, we've chosen to use a 1/3 rate turbo-coated binary phase shift keying with non-return to zero. The Jet Propulsion Laboratory of the U.S. has recommended this scheme for deep space communication links because it trades off very bad spectral efficiency for a very low SNR requirement. This modulation scheme actually only requires a half dB of signal-to-noise ratio, and with this you get 1 bit per second for every 60 hertz of bandwidth that you use. So with this, from 10.5 light years away, we can achieve anywhere between 7.5 bits per second to 23 bits per second, depending on how far we are away from the sun.
For the embedded system part, we will use a microcontroller and some memories, which are space radiation hardened component, as well as the 3 devices that we will use for the imaging, which are one is an ultraviolet imaging spectrometer, another two which is an infrared thermal imaging, and the last one a high scientific camera system.
Thermal control engineering will be very critical to this mission, mainly because at some points of the mission we will be very close to the star and at other parts we will not. To make up for this vast temperature difference, there are several devices that will be used on board our spacecraft, including heaters to heat the batteries, louvers to remove any heat that could be in the system, coatings for the outside of the spacecraft to keep radiation out of the spacecraft from the star, and also MLI blankets, multi-layer insulation around the components that need to have protection.
Equally as important as thermal and radiation control, the electronics on the spacecraft will have to endure vibration, acceleration, and shock conditions. In order to meet these, to survive these conditions, the electronics on board the spacecraft will have to use military and space-grade components with very rugged enclosures and mounts to keep the electronics safe. Also important is the reliability of the electronics, because they have to work for a very long lifetime of the spacecraft. The electronics will have to have many redundant systems built in.
Thank you for listening. Now please enjoy these demonstrations that were created by our very own Emmanuel.